So, welcome to problem 2. So, the first thing is, there's an error in the parenthesis here, that I have never had the discriminant defined for a non-monomial polynomial. They were always monomial, so a naught was equal to unity. I checked with Mabel, and this is actually correct. That's the usual definition. So, or that rather that is not the definition. The discriminant of f see if this works better. Yeah, that's nice. It's the product of the derivative of the roots and this doesn't depend on the leading coefficient, or it does depend on the leading coefficient. So this gives a to the nth, and if this is that is, if it's equal to this by Vandermonde's theorem, then this should give a naught to the nth here and a naught to the nth. So we should multiply it by 8 minus n plus 1. No, 8 to the minus, this 8 to the minus first. So easy now, easy now. There we go. Easy does it. So this one gives a to the nth and then a to n minus 1, and that's what we have here. So I believe that then they agree by Vandermonde's theorem. There we go. So I just needed to clarify this. So we have two examples we have to work on. One is G2 equals 4. Start down here. G3 vanishes. Oh, it's X. So we have the roots plus minus 1 and naught. Of course, there's some vanishes and their product vanishes, and this guy becomes, or the second order, it's minus 1, and that's squared in here times the leading coefficient, so everything seems nice. And then we compute this directly. That's 16 times 1 times 1 times 4, that's 64. And this should be equal to the unknown alpha times g2 to the third, and g2 was 4. That gives alpha equals unity. I forgot something here, didn't I? A naught in squared, that's 16, times 4, that's 64. Seems to be unity rather. And next case, yeah, let's just correct it with this guy. Minus 4. So here we have the roots 1 omega squared This is actually slightly more involved. So the discriminant is 16 times. Did I square this guy? Yes. 1 minus omega squared, 1 minus omega squared, and omega minus omega squared. This one I can do. Yeah, I am doing what he wrote. So let's work on it up here. Let's try to do it 1 plus omega squared minus 2 omega times 1. So this is omega squared. Omega squared to the second is omega to the fourth. I'm working on this one. So omega squared to the squared, that's omega to the fourth, it equals omega. So it's plus omega. And this is omega times 1 minus omega. This is annoying, really. Of course, we could go into Mabel and do it. Let's try to expand it. We will be using 1 plus omega squared equals naught. And that's 1 plus this plus omega. So this gives minus omega, so we have minus 3 omega times, this gives minus omega squared. So that's 9 omega to the third. I was very convinced that the discriminant was real. And oh, that's not the discriminant. It has to be, oh, I have squared it. Now, that was very dumb. That was very dumb. We should first just compute the product and then square it. So let's do that as a kind of check. So first these two, 1, and this gives unity. So it's 3. It appears that I forgot this. So check this, or no, this is without. No, I squared the two first ones, but I forgot to square the second ones. Omega to the second plus omega to the fourth minus what is called the double product. That's 2. This gives -1, so it's -3 minus 27. Right. So the discriminant was real, -27. And that should be equal to G3 times G2 vanishes, so beta G3 squared. Which, and G3 equaled 4, so it's beta times 16. Actually, it turned out that I forgot 16 here. So the 16 here should be multiplied all the way through. So it should be times 16. So we just end up -27. So I actually did this on Mabel before starting the exercise, plugging in the polynomial and having it compute the discriminant. And I got 16 times as much. Unity for alpha and -27. That times 16 should give -432. So there's a factor 16. Doing what he says here, I think gives my result, and I don't quite understand. Thought the other one was correct too, because they have the same definition. At the moment, I find nothing wrong. I have scrutinized very much what I've done, the toughest judge in the world, and I declare myself innocent.